Okay, so here is our last lesson of chapter 3. It's a completely imaginary chapter. Our section 3.9 doesn't really exist. However, I made a lesson for you on augmented matrices because this is the preferred way using matrices to solve systems of equations. Okay, so first objective, to solve a linear system by writing it in triangular form. You'll see how simple and fast it is to solve a system of equations when it's in triangular form. Objective 2, perform what we're calling elementary row operations on an augmented matrix. We've seen that word augmented matrix before, and it means to add a row or a column of numbers. And then finally, number 3, to solve a linear system of equations using augmented matrix. So we've solved it by hand substitution elimination. We've solved them using Cramer's rule, an inverse matrix, and now here is our final way to solve a system of equations with augmented matrices. So our first objective, take a look at that picture. It looks pretty sweet. I would live there. You can see all these triangular patio looking things, and what we're doing here in this objective is being able to solve a linear equation when it's in triangular form. Okay, so take a look at this first exercise. We're going to solve this system of equations. And if I look at this, sure, it has x, y, and z, but say the second equation here doesn't have any x's in it, and the third equation doesn't have x or y in it. And that makes this thing very, very easy to solve. For example, I already have my answer for z. So if I wanted to find y, just take that 3, stick it in for z in the second equation, and I can get y really quickly. So y plus 2 times 3 is equal to 5. Y plus 6 equals 5, so y is equal to -1. Okay, and then finally by substitution I can put both of these into the top equation to find out what x is. So x minus 2 times -1 plus 2 times the 3, all this is equal to 9. Let's just simplify here. So x plus 2 plus 6 is equal to 9. That's 8. Subtract the 8 over, so x is equal to 1. So I have the answer 1, -1, 3. Look how easy that was to solve. And this system of equations is in what we're going to call triangular form. Okay. So two systems are equivalent to each other if they have the same solution. Now, if I look at these two linear systems here in x, y, and z, they don't look too much alike, other than they both have the same first equation. It's just that they have the same answer. If you were to solve the one on the left, solve the one on the right, you'd have the same answer, and that's why we call them equivalent. Okay, it's just that the one that's on the right is an easier one to solve, especially if we're doing it by hand. Okay, and this is the one that we call in triangular form. So here is what triangular form is. So the equations have a stair-step pattern, right? I've got 4 things on the next one, on the top one, 3 things on the next one, and 2 things on the bottom thing, right? Okay, and the leading coefficient of each of the equations is 1. It's called triangular form because you can see over there on the left-hand side it makes a triangle. And we saw how easy these things were to solve if it's in triangular form. Okay, so the question might be, well, how do I get it into triangular form then? If I have one that's not in triangular form, how do I put it in that form? Okay, and so the answer involves doing elementary row operations, otherwise known as Gaussian elimination. It's called Gaussian elimination because it's named after that guy, Carl Gauss. I think we may have mentioned this guy before in another lesson. Very famous mathematician, really super smart guy. And we're going to see him again whenever we talk about the fundamental theorem of algebra, because he was the first one to prove that too. Okay, so these are our elementary row operations. Okay, so the first one is I can take any 2 equations and I can interchange them. Whenever I give you 3 equations, it doesn't matter which one comes first. Just like whenever you use slope, the slope formula to find the slope between 2 points, it doesn't matter which one is first as long as you keep it consistent on the top and the bottom. It's the same kind of thing. So you can switch any two equations and you produce an equivalent system. Okay. The next thing that I could do is I can multiply any one of my equations by a non-zero constant. Like if I have an equation and I divide everything by 2, then I still have an equivalent equation. I would still have the same answer. It's just that the numbers have changed. It's equivalent. Okay, and then the last thing that I can do, this is the strange one. It's I can add a multiple of one equation to another equation to replace the latter equation. Huh? Look at what is written on that circle there. 2a plus c. So I can take equation A, multiply it by 2, add it to equation C to replace equation C. Okay? And that's the key difference between this method and, say, doing it by regular elimination. When we did it by regular elimination, we made a new equation. We didn't replace the old one. And what we're doing here is we're replacing the old equation. So these are the three things that we can do to create an equivalent system that might be easier to solve. Okay? So let's take this system of equations and rewrite it in triangular form using these elementary row operations. Okay, so I'm going to just label them A, B, and C just like I did way back before whenever I was solving these things by elimination. Okay, so step number 1 is you want to eliminate the x in all but the first equation. Okay, and I say first equation because it has an x with a leading coefficient of 1, and I kind of want that. If I didn't have that one, let's say equation C was where equation A is, I could just switch the order of that and make it a little bit easier on myself. Okay, so the first thing that I'm going to eliminate then is this x in that position. So in order to get rid of that x, I can just add up equation A plus B. And so that's exactly what I'm going to do. But remember, whenever I do this, I'm going to use that to replace equation B. Okay, so equation A stays the same, equation C stays the same, but I'm going to have a new equation B formed by adding A and B together. So let's think about, before I put it up here, what that new equation B is going to be. Okay, I'd add up x and negative x, it'd be gone. Negative 2y plus 3y will give me just 1y. 2z plus nothing gives me 2z. And then finally 9 minus 4 gives me 5. So notice that the top equation stays exactly the same as that top equation. The bottom equation, we didn't do anything else to it either. I just replaced equation B with A plus B. Okay? And I got rid of that x. Now I need to get rid of this x. In order to get rid of that x, I can't use equation B on it anymore because there's no x in there. I have to go back up to the top equation and do something with that in order to find, in order to get rid of that x. So I can do that by taking 2 times the top one, actually negative 2 times the top one, and adding it to c. So negative 2a plus c is what we're going to do. So just for visual reasons, I'm going to multiply everything in the top equation by 2. Whenever I write down my equivalent system, though, I want to keep the original equation A, though. Okay, so let's go ahead and times everything in the top equation by 2, and this is just going to be making it easy so that I can add up those those elements. So the negative 2x plus the 2x, they'll cancel out, and I won't have anything. 4y minus the 5y, I'm going to have a negative y. Negative 4z plus the 3z, I'm going to have a negative z. And then a negative 18 plus a 16 is going to give me negative 2. So again, notice that the top equation didn't change. The middle equation didn't change. I just replaced equation C with negative 2a plus c. Okay, so I've just done the first step, which is to get rid of the x's in the second and the third equation. The next one, to make this thing in triangular form, is to get rid of the y in the last equation. Okay, so that's the next step. So to eliminate the y in the last equation, the only thing that I can combine it with is the middle one, equation b, because it's the only one that has just a y in it with the z. If I used equation a with it, it would reintroduce an x, and I don't want that. Okay, so maybe you can see that to get rid of the y in that bottom equation, I can just add up b plus c to replace equation c. Okay, a will stay the same, b will stay the same, but my new equation for c is going to be no y's, because they will cancel. 1z is equal to 3. And so now I've just put it in triangular form, and that's the same one that we solved back on exercise 1. Okay, so what we've just done is use elementary row operations to turn a system of equations into its triangular form. So here are the steps involved, some helpful steps in writing your system of equations in an equivalent form called triangular form. So step 1, you're going to eliminate x in all but the first equation using those elementary row operations. Step number 2, you're going to eliminate y in the last equation. Okay, so then we'll have x, y, z in the top, y, z in the middle, and just z by itself on the bottom. And then if I have to, on step 3, you're going to use multiplication to make all the leading coefficients a 1. Okay? And that will put it into triangular form.